All right, so this is the groundwater presentation, but first a few quiz questions. So I'll give you a moment to look over the question, and then I will include the answer. All right, so recall that discharge is the amount of water that is passing a given area per second. And so C would be the answer. The larger the flood, the 100-year flood would have a higher discharge. Okay. We don't know exactly what the discharge number is, but it would be the highest value. Question 2. All right, so permeability is the ability of a solid to allow fluids to pass through. Question 3, following term describes the total sediment load carried by a stream. Recall that these are two words here that people often confuse, capacity and competence. This is capacity, whereas competence is the largest or the more massive, most massive material that a stream could carry. So A is the correct answer. All right, finally got to do a little math on this one, but you should be able to do that quickly in your head. All right, so in this example, our area is 8 times 6, which is 48, but we have to also multiply by the velocity, 3 feet per second. That gives us 144 cubic feet per second, T. All right, so this is about, I should switch the view here. This is the groundwater presentation. All right, so we already talked a little bit about groundwater as one of the phases of the water cycle. We call it as the third largest reservoir of fresh water on the planet. And it's the process of infiltration by which the water enters into the ground. And we've looked at porosity and permeability a little bit, and those are the two keys here when we're talking about infiltration and groundwater movement. So porosity is the empty space between pores. So imagine a lot of larger size sediment, gravel for example. There's some negative space or empty space between the pieces of gravel. Those would be the pore space. So how much water stays in that pore space is porosity. Whereas permeability is the movement and the transfer of the fluid through that space. All right, so at this point, there's another video that coincides with the porosity and permeability investigation. So I think you should pause this presentation, jump over and do that lab, and then come back to this one. All right, so hopefully you did the lab before this. If not, I guess this will still work, but that's probably the preferred way to do it. So you may have found that generally there's a connection between porosity and permeability. High permeability tends to coincide with high porosity. There are some situations where that is not true. Look at some of those. Well, I'll just say it here because I'll probably forget. Something like a solid rock is going to have a low porosity, but if there's a crack that goes through it, then the water can still flow through that crack, right? And so it can have low porosity but high permeability as the water goes through the crack. It's just the rock itself is not holding much water. All right, so when we talk about beneath the surface as water infiltrates into the ground, we're looking at three things in this picture: the unsaturated zone and the saturated zone, which for whatever reason, sometimes people mix those up. And so it's important that we get those together with what those mean. They are separated by the groundwater table, and that's probably the important thing to focus on, the groundwater table. So what that means is as the water infiltrates into the ground, right, it goes deeper and deeper and deeper, pulled towards the center of the earth due to gravity, And so it fills into the saturated zone. And so that's what the saturated zone is. If we look at the pore space there, it's saturated. Water fills up that pore space. If we move above the groundwater table, then we have some air stuck in there. So this would be akin to, just imagine that you're trying to drink something out of a straw, and you get air in the straw, but you also get some of the fluid that you're trying to drink, right? It's that annoying thing that can happen. But if you have that happen, usually what you do then is push the straw a little bit deeper into your cup, and then you're trying to get into that saturated zone where you're just getting the liquid and not any air mixed into the straw. So same thing here. That's the zone where we want to, if we're going to drill a well, we want to get into that saturated zone. All right, so we see it again here, but this shows that even a deeper cross-section of the interior of the Earth. There is a point, right, where we move within the Earth that it gets into bedrock where the porosity is just going to be too low, right? It's just solid rock, and so there's going to be low porosity there. All right, so we have a zone where there is porous rock saturated with fresh water. And this, as we go deeper and deeper, gets to be the point where there's not enough water between the pore spaces, low porosity. All right. So there is a depth at which we aren't going to see much in terms of water within the pores. Okay, but don't mistake this with the previous slide, right? So there's that top zone of unsaturated. Beneath that, we get into these saturated zones. All right, so here's what we basically found from the lab for the most part, although we looked at just a few materials there. And I should say that in the lab, the one material that you looked at was the cat litter. And so that was just an outlier because of the way that cat litter is designed for what it's designed for. It has very high porosity, but very low permeability, right? It's meant to trap the fluids. All right, so this, just a few more terms here. Zone of saturation. That's what we've been speaking about. The zone of aeration, really that unsaturated zone. The water table we looked at, that's the separation between the two. Recharge is what it sounds like, right? In times of precipitation where water is infiltrating into the saturated zone. And then the aquifer really is that saturated zone, and there are different kinds of aquifers. So we're going to focus on the first two kinds of aquifers, but I'll mention a third. So unfortunately, they go by different terms depending on, I guess, the resource. So unconfined and confined. So probably best shown together. The confined is probably easier to explain first. Here we have this zone that is confined by an impervious surface. Right, so this layer of shell, this aquitard, is not allowing water to pass through it. And so this water in the pore space beneath is confined. It can't move up through that. Right? Whereas if we look at the unconfined aquifer, there's nothing above it confining it. It's confined from below, but that's not of importance because we're trying to bring this groundwater back to the surface to use. And so if we were to drill a well into these two surfaces, the top would be unconfined and the bottom would be confined. Right, the third type is the perched aquifer. I'm not going to mention too much about that, but it's just a regionalized aquifer zone. All right, so as I said, there are different terms for these. The artesian aquifer to replace the confined aquifer. So it is bounded by impervious layers on both sides. So because of that, it's under pressure, and so I like this picture because it shows that. So right here is what we're looking at is the confined aquifer, or the artesian aquifer. It's confined on both sides. And we have a well over here that is drilled into the artesian well. Above that, we have an unconfined layer, and so we have a non-artesian well. So this is the well that you most likely have in your house if you live in a house or have lived in a house with well water. It's this one. And so what the non-artesian well is, it means that you need to uh, provide power. You need some way to get that water up that well shaft, and we do that with electricity. So if you live or have lived in a house with a well, you know that if the power goes out and you don't have a backup generator, that you don't have water, right? Because you need electricity to pull this water out. That is different than the artesian well or artesian aquifer. That water is under pressure, and so you don't need to have power to bring that water to the surface. So that's shown by this person here. I know this is a foreign concept to most college students, but here we have a fluid being poured into a funnel into a hose, right? And so because of that, because of the elevation change, it's at this incline, is under pressure. So at the end of the hose, or here, there's a hole in the hose, the fluid comes out under pressure rather quickly, right? And so that's what's happening here at the artesian aquifer, okay? Because it's being pulled down by gravity, it's under pressure, and we don't have to provide any power to get that water to the surface. So that's essentially a spring, something like that. All right, so I'm going to stop here, and then I think in a separate presentation we'll talk about how we can look at the movement of water through the surface.